In the closing months of 2025, volcano watchers scrolling through eruption reports could have been forgiven for feeling a little uneasy. Ethiopia's Haile Gubby erupted for the first time in recorded history. Indonesia's Lewatobi Laki-Laki sent ash miles into the sky. Kamchatka's Kluchevskoy roared back to life. Reports rolled in from Africa, from Asia, from the Americas, seemingly all at once, arriving in the same general window as a genuinely turbulent stretch of solar activity, a run of major flares and geomagnetic storms that had already been making headlines of its own. The coincidence was striking enough that it was almost impossible not to ask the obvious question out loud: is the sun somehow shaking the ground beneath our feet? This is the story of that question, what the actual scientific record says about a possible sun-volcano connection, and why the honest answer sits in a far more interesting and far more uncertain place than either a confident yes or a dismissive no. To take this question seriously, and it deserves to be taken seriously rather than waved away, you first have to establish something surprisingly difficult to pin down with confidence: whether global volcanic activity is actually increasing at all, in any statistically meaningful sense, rather than simply appearing to increase because more people are watching more closely than ever before. This is not a trivial distinction, and it is one the scientists who track volcanic eruptions for a living have spent decades grappling with directly. The Smithsonian Institution's Global Volcanism Program has maintained the world's most comprehensive database of volcanic eruptions since 1968, compiling records that, for well-documented large eruptions, stretch back centuries further still. When researchers there have examined the long-term eruption records specifically looking for genuine trends, their conclusion has been consistent and specific. There is no solid evidence that volcanic activity itself is actually increasing over time. What has increased, dramatically, is the world's ability to detect, document, and report volcanic activity that, in earlier centuries, would have gone entirely unnoticed by anyone outside the immediate region, or would have been recorded only in dull, fragmentary local accounts that never made it into any global database at all. More people now live near active volcanoes than at any point in human history. Satellite monitoring, seismic networks, and instant global communication mean that even a modest eruption on a remote, sparsely populated volcanic island now generates data and news coverage within hours, a level of documentation that simply did not exist even 50 years ago, let alone a century or two back. The Global Volcanism Program's own analysis makes a specific, telling point on exactly this question. The best evidence that apparent increases in activity reflect improved reporting rather than a genuine geological trend comes from looking specifically at the record of the largest eruptions, the kind whose effects are significant enough and far, reaching enough that they were extremely unlikely to escape documentation even in earlier centuries, even in remote parts of the world. That subset of the historical record, the genuinely large eruptions least vulnerable to reporting bias, has remained remarkably constant over the past 2 centuries, showing none of the dramatic upward trend visible in the raw, all-inclusive eruption count. In other words, the apparent spike in global volcanic activity that so often shows up in casual observation and in the kind of rapid-fire news roundups that can make several unrelated eruptions on different continents feel like a single, connected surge, is very largely an artifact of better bookkeeping, not a sign that the planet's interior has become more restless. That is an important, necessary caveat, and it deserves to sit at the center of this discussion rather than at the margins. But it does not fully close the book on the underlying question because a separate, more specific body of scientific research has spent decades investigating something narrower and more precise than, is the world getting more volcanic? Whether the sun's roughly 11-year cycle of rising and falling activity shows any statistically measurable correlation with the timing of volcanic eruptions, independent of the broader reporting bias problem. And here, the honest answer is considerably more complicated than either a confident yes, obviously, or a dismissive no, that's nonsense. A handful of published studies, spanning several decades of research, have reported statistically significant correlations between solar activity cycles and the frequency of volcanic eruptions. Some of this research has focused specifically on sunspot numbers, the most commonly used proxy for overall solar activity, examining eruption records stretching back more than a century and finding patterns that appear to track the roughly 11-year solar cycle with real statistical significance. Other researchers have gone further, comparing volcanic eruption frequency against the sun's own background magnetic field structure rather than sunspot counts alone, reporting a notably strong positive correlation. In one analysis, a correlation coefficient of 0.84 between the timing of eruption peaks and specific phases of the solar magnetic cycle, along with a dominant, roughly 22-year periodicity that matches the sun's full magnetic polarity cycle rather than the shorter 11-year sunspot cycle alone. Interestingly, several of these studies have found their relationship running in a direction that surprises people encountering this topic for the first time. Rather than volcanic activity peaking alongside solar maximum when the sun is at its most active, multiple analyses have instead found eruption frequency trending slightly higher during the declining phase of the solar cycle, or even during solar minimum itself, when the sun's activity is at its calmest. That detail matters enormously for evaluating the intense solar activity directly causes eruptions, framing that tends to circulate in more sensationalized coverage of this topic, because, if anything, several of the more carefully conducted studies point toward a correlation running in the opposite direction from what a simple, dramatic cause and effect story would predict. That surprising directionality is itself a clue toward the biggest, most persistent problem sitting underneath this entire body of research. Even where statistical correlation has been reported, and reported by researchers working carefully and publishing in legitimate journals, no one has yet identified a physical mechanism capable of explaining, in concrete, verifiable terms, exactly how variations in the sun's output could plausibly trigger an eruption from a magma chamber sitting many miles beneath Earth's crust. This is the single largest gap separating a statistically interesting correlation exists in some datasets from the sun causes volcanic eruptions. And it is a gap the researchers publishing this work have, in the more careful papers, been genuinely candid about. One study examining the volcanic magnetic field correlation explicitly acknowledged that the physical reason behind the pattern they identified remains difficult to fully explain, offering it as an intriguing statistical finding worthy of further investigation rather than a settled, mechanistically understood causal relationship. That absence of a clear mechanism is not a minor technicality. In the physical sciences, a statistical correlation without a plausible causal pathway is treated as suggestive at best and often as coincidental until proven otherwise, particularly in a field like volcanology, where the actual physical drivers of eruptions are already reasonably well understood and involve almost none of the physics that would connect them to solar output. Magma moves toward the surface driven by buoyancy, by the release of dissolved gases as pressure drops, by the physical rupture of overlying rock under accumulated pressure, and by the slow, tectonic processes of plate movement that build the stress conditions leading toward an eruption in the first place. None of those processes have an established, well-characterized pathway connecting them to solar irradiance, sunspot activity, or the sun's magnetic field, the way, for example, the well-documented physics of the mammalian diving reflex explains why holding your breath slows your heart rate, or the way well-established atmospheric physics explains why greenhouse gases trap heat. There is, however, a genuinely well-established, mechanistically understood example of an external astronomical force measurably influencing volcanic behavior. And it is worth including here specifically because it shows what a legitimate physics-backed correlation in this space actually looks like, in contrast to the murkier solar research. Multiple peer-reviewed studies have documented tidal modulation of volcanic activity, meaning the gravitational pull of the moon and sun, the same forces responsible for ocean tides, measurably affects the timing of small eruptive events and volcanic tremor at certain highly active, frequently erupting volcanoes. Research at Stromboli, the persistently active Italian volcano, famous for near-continuous small explosions, found a real, statistically robust correlation between the timing of individual explosive events and the tidal cycle, and similar tidal modulation of volcanic tremor has been documented at other well-monitored volcanic systems as well. Crucially, this tidal effect comes with an actual, well-understood physical mechanism attached to it. Gravitational tidal forces physically stress the rock and magma within a volcanic system, in the same well-characterized way they stress the ocean's water and at a volcano already primed and ready to erupt. Sitting right at the threshold of releasing pressure, that small additional tidal stress can plausibly serve as the final trigger, tipping an already imminent eruption into an actual explosive event. That tidal mechanism offers a useful template for what a genuine, physically grounded external trigger for volcanic activity looks like. A real, measurable force, a known physical pathway by which that force could plausibly influence an already primed volcanic system, and a modest, modulating effect on timing rather than a claim that the force is single-handedly generating eruptions that would no otherwise occur at all. The solar volcanic research, by contrast, has generally struggled to clear that same bar. Solar irradiance reaching Earth's surface varies only slightly across the solar cycle, nowhere near enough to plausibly heat rock miles underground in any physically meaningful way. The sun's magnetic field and the particle streams associated with geomagnetic storms interact with Earth's own magnetosphere and upper atmosphere, not with the solid rock of the crust and mantle, leaving genuinely unclear how such an interaction would translate into pressure changes deep inside a magma chamber. Some researchers in this space have proposed more speculative pathways, involving subtle electromagnetic or electrical effects on rock stress at depth, but these remain considerably less developed and considerably less broadly accepted within the mainstream geophysics community than the well-established tidal mechanism. It is also worth being precise about the specific run of eruptions that likely prompted this question in the first place, because examining them individually tends to undercut the idea of a single, connected, solar-triggered global event. Ethiopia's Haile Gubby volcano erupted for the first time in recorded history in late November of 2025, a genuinely significant event, but one occurring along the East African Rift, a tectonic system actively pulling apart independent of anything happening 93 million miles away on the Sun. Indonesia's Lewotobi Laki-Laki, meanwhile, sits along the Pacific Ring of Fire, an entirely separate subduction zone system with its own long, well-documented history of eruptive activity extending back years before this particular active period. Kamchatka's volcanic activity, including notable stirring at Kluchevskoye, followed the same major regional earthquake that had already independently rocked the area in the summer of 2025, a well-understood geological relationship, since powerful earthquakes are known to sometimes trigger or accelerate volcanic unrest in already primed systems nearby, an established stress transfer mechanism entirely separate from anything solar. Each of these eruptions has its own well-documented, tectonically grounded explanation, rooted in the specific geological system it belongs to, and none of them requires reaching for a distant, mechanistically unproven solar trigger to make sense as an individual event. What connected them, in the public's perception, was primarily timing and visibility. Several notable eruptions clustering within a period of weeks or months, amplified by rapid global news coverage and social media, arriving in a stretch of time when solar activity also happened to be making its own separate headlines because of an unusually active stretch of the current solar cycle. That kind of temporal clustering, several independent, geologically unrelated events happening to occur close together in time, is exactly the sort of pattern the human brain is exceptionally good at noticing and exceptionally bad at correctly evaluating for statistical significance, a well-documented cognitive tendency, sometimes called apophenia, the perception of meaningful connections between genuinely unrelated events. It is the same underlying tendency that makes coincidental clusters of any kind, from cancer cases in a neighborhood to a string of celebrity deaths, feel far more statistically remarkable than they actually are once a proper baseline rate of the underlying event is accounted for. None of this means the broader scientific question is entirely closed or unworthy of continued study. Legitimate researchers do continue publishing on possible solar-terrestrial geophysical connections, examining everything from the solar cycle's debated influence on Earth's climate to more speculative proposed links with seismic and volcanic activity. And that ongoing research deserves to be engaged with honestly rather than dismissed outright simply because it has not yet produced a settled, mechanistically confirmed answer. Science regularly begins with an observed statistical correlation long before the underlying mechanism is fully understood, and dismissing every unexplained correlation out of hand would have delayed the eventual understanding of plenty of now well-established phenomena. The honest, current state of the solar volcanic question sits specifically in that unresolved middle ground, a handful of statistically interesting correlations, reported by legitimate researchers in peer-reviewed venues, sitting without a confirmed physical mechanism to explain them, layered on top of a broader eruption record that, once corrected for improved global monitoring and reporting, shows no clear evidence of an actual overall increase in volcanic activity at all. That is a considerably less dramatic conclusion than the framing, "the sun is triggering volcanoes," implies, but it is also, in its own way, a more genuinely interesting place to end up because it captures something true about how science actually handles a provocative, headline-ready coincidence. The right response to a striking correlation is neither uncritical acceptance nor reflexive dismissal. It is the harder, less satisfying work of asking whether the baseline rate of the underlying events, viewed without the amplifying effect of modern global news coverage, actually shows the pattern being claimed, and if a real correlation does hold up under that scrutiny, searching honestly for a physical mechanism that could explain it exactly the way researchers have already done successfully for the well-established tidal triggering of volcanic tremor. Until solar volcanic research clears that same bar, the most accurate answer to the striking cluster of eruptions that closed out 2025 remains a geological one, tectonic plates and magma systems around the world doing what they have always done, independently of each other and independently of the sun, simply happening. This time, to do it in a window when the rest of the world was also watching an unusually active sun with genuine, well-earned scientific interest of its own. It is worth spending a little more time on why this particular kind of claim, a dramatic, astronomical trigger for a dramatic geological event, tends to resurface again and again across the history of both scientific inquiry and popular science communication, because the pattern is considerably older than the current solar cycle, long before anyone had modern seismometers or satellite-based solar monitoring. Observers across many cultures noted apparent connections between celestial events and earthly disasters, comets, appearing before plagues, eclipses preceding wars, unusual planetary alignments blamed for earthquakes. Most of those historical claims have not survived rigorous modern testing, not because ancient observers were foolish, but because the human tendency to notice and remember striking coincidences, while forgetting or never even registering the far more numerous instances when a dramatic sky event was followed by nothing unusual at all, operates just as powerfully today as it did centuries ago. Modern global media simply supplies that same cognitive tendency with an enormously larger and faster stream of potential coincidences to notice, drawn from the entire planet rather than a single observer's local region, which paradoxically makes striking seeming clusters of unrelated events considerably more likely to occur and be noticed, purely as a matter of statistics, even though no new underlying physical connection has been added to the picture at all. That statistical reality is worth making concrete with a simple thought experiment. At any given time, the Smithsonian's Global Volcanism Program typically tracks somewhere between 40 and 50 volcanoes in a state of continuing eruption worldwide, with roughly 20 of those actively erupting on any particular day, spread across dozens of countries and several entirely separate tectonic systems. Given that baseline level of near-constant global volcanic activity, some subset of those systems producing a notably visible or newsworthy event within any given few-week window is not a rare, remarkable coincidence requiring a shared external trigger. It is close to the expected, statistically ordinary behavior of a planet that, at essentially all times, has multiple volcanoes doing something worth reporting somewhere across its surface. The question worth asking is never simply, did several eruptions happen around the same time as a burst of solar activity? Because the answer to that question, given how frequently both eruptions and solar activity bursts occur, will very often be yes, almost by default. The far more demanding and far more scientifically meaningful question is whether eruptions cluster around solar activity more often than pure chance alone would predict, tested rigorously against the full historical record rather than a single, recent, headline-friendly cluster. And that is precisely the harder statistical question the legitimate published research on this topic has been attempting, with genuinely mixed and still unresolved results to answer. There is a final point worth making about why getting this specific distinction right matters beyond simple scientific accuracy. Because how a society understands the relationship between solar activity and geological hazards has real practical consequences for how resources get allocated toward genuine risk. Volcanic hazard monitoring is a resource-intensive, genuinely important field, one responsible for real early warning systems that have saved lives at well-monitored volcanoes around the world. If public attention and, by extension, funding conversations become oriented around an unproven, mechanistically unexplained solar trigger, that attention risks being diverted away from the well-established, well-understood monitoring priorities that actually protect people living near active volcanic systems. Seismic networks tracking the magma movement that reliably precedes eruptions. Gas monitoring stations tracking the sulfur dioxide and other volcanic gases that signal rising unrest, and ground deformation measurements tracking the physical swelling of a volcano's surface as magma accumulates beneath it. None of those proven life-saving monitoring tools have anything to do with solar activity. All of them depend on sustained, well-funded, scientifically grounded attention to the actual, physically understood processes driving volcanic behavior, the same tectonic and magmatic processes that, on their own, fully explain the eruptions that made headlines at the close of 2025. Without needing to look 93 million miles away for an explanation, the evidence simply does not yet support. None of this is to suggest the underlying curiosity driving the original question is misplaced. Wondering whether the sun and the solid earth beneath our feet are connected in ways not yet fully understood is a genuinely reasonable scientific instinct. And it is worth remembering that plenty of now accepted geophysical relationships once sounded just as speculative before the mechanism connecting them was finally worked out. Continental drift was dismissed by much of the geological establishment for decades after it was first proposed, precisely because no one could identify a physical mechanism capable of moving entire continents until the discovery of plate tectonics and seafloor spreading finally supplied one. The lesson from that history is not that every unexplained correlation deserves to be treated as settled science before its mechanism is understood, but that the process of taking a strange correlation seriously enough to keep testing it while resisting the urge to declare it proven ahead of the evidence is exactly how the genuinely real connections eventually get separated from the ones that turn out, on closer inspection, to be nothing more than coincidence dressed up in a compelling narrative. For now, the solar volcanic question remains open in exactly that sense. A handful of intriguing statistical studies, a well-documented and mechanistically understood cousin in the form of lunar and solar tidal triggering, and a recent cluster of headline eruptions that, examined individually, each traces back cleanly to its own well-understood tectonic cause. Whether some subtler, still undiscovered solar influence is quietly operating underneath all of that remains a legitimate question for future research to keep testing. What the current evidence does not support is treating that possibility as an already confirmed explanation for why several volcanoes, on several different continents, happen to make news within the same few weeks of an active solar cycle. Sometimes a striking coincidence really is just that, a coincidence, and the discipline of checking carefully before assuming otherwise is not a dismissal of the question. It is the question being taken exactly as seriously as it deserves,